we could just run through them and give a little bit of background to the theory as we're going down. So we should be able to get through all of them. And now you've done the course a bit, you should be a bit more comfortable now when we go through these. So as the course builds on, what we saw earlier should seem easier. So the first question then was about general nonlinear regression models and the assumptions we make. So it has skipped a bit of detail here. I guess it was using a lot of the notation and the setup in the lecture, so it should have given a bit more detail, but you could really take it from the lectures. What it's saying is that assume we've got some dependent variable y, which is some function of x, call it m of x, plus e. Plus, I think it's e here. It's not actually said there. What it's saying is where we assume, so we've got a linear where it assumes that the conditional expectation function model assumes this, that this here equals not, and it's assumed that the variance, well, it's not even really an assumption, we're just to state that the variance of e given x is sigma squared x. And again, this holds for all values of x. So this is not really, well, this is a very mild assumption. This is not assuming homoscedasticity here, it's just defining the variance of this unobservable for a given value of x as sigma squared x. So it could vary with x, so there may be heteroscedasticity. The key assumption then is that this unobservable has conditional mean equal to naught. What that means is, this is just equivalent to saying, if we take this model and this assumption here, so if we call this 1 and this 2 and then 3, well, 1 and 2 just imply, well, take conditional expectations on both sides, we just plug in y, so that's the first assumption. So what it's saying is, in essence, this mx could be any nonlinear function of x, take conditional expectation, so I need to do the conditional expectation here, and then we've got the conditional expectation of the sum of two terms, so it's each one, it's a sum of them added together, so all the properties of the conditional expectation function are the same as for the unconditional, plus e of e given x. And what's this term here, the first term? So is everyone still listening? So I can't see the rest of it. I can only see the chat now. I'm working just from my Surface, so I can't see anything apart from the chat screen. Well, this when we condition on x, x is fixed. So the first part is just mx, and we've assumed that the other term is not by assumption 2. So we can see then that the two of the assumptions together, this is just equivalent to saying then these two assumptions 1 and 2 are equivalent to e of y given x equals m of x. So all we're saying is that this conditional mean of y given some value of x is equal to m of x. So this is a very mild assumption. We've not said what the form is. It could be anything. It could be any nonlinear function. So the linear model, for example, assumes that this, in the linear model, we assume that m of x equals x transpose beta. Again, we've skipped some details here, but x you can think of is going to be a p by 1 vector, which could include, say, all personal characteristics of some person or a country. So they think of there's p, it's a p vector, there are p elements in it. So again, this will be the linear model. But there's no reason why it should be linear. In general, this could be a nonlinear function. We could have that m of x is the exponential of this, for example. In that case, that wouldn't be a nonlinear model. Or we could have equals 1 over the apps, whatever. Any nonlinear, and it could be something really complex. So the question then really, the first bit is asking you to look at the relationship between the conditional and the unconditional variance. Well, this is just a general statistical result. So the first bit asks to show that sigma squared, the unconditional variance of e, is equal to the expectation of sigma squared x. And it means take expectations with respect to the distribution of x. So we often omit this. We just infer what the expectation taken across. But because this is just a function of x, where x in general it could be some random variable, we take the average across x. Well, this is just the law of iterated expectations, right? The solution the solution that you're given use the fact that we assume the conditional mean of e given x is not, but actually it holds in general, and we can see that because remember, well, sigma squared is just the variance of e, which remember the definition is the expectation of e minus its mean squared. And if we expand all this out, we get e of e squared minus the average of e all squared. So remember, note the difference. We've got the average of e squared. So take e squared and then take the average of it, or find the mean of e, whatever that is, and then take the square of it. So this is the next bit. So again, we're going to assume that that's not, but in the result actually holds in general. This is just a general result. It says that the unconditional variance of any variable is just the average of the conditional variance, and that just holds by the law of iterated expectations. Sigma squared x, the formal definition, well, it's just the shorthand is variance of e given x, and the definition of this is, well, e squared, and now we take the deviation from its conditional mean, again condition on x, and if we expand all this out, it's got the exact same form of the unconditional e given x squared. Okay, and we're going to assume that we've assumed in our model that e of e given x is equal to naught, which would, well, in this equals this, it's equals to naught. So, well, we've assumed that this equals naught, and this implies that the expectation of e equals naught. You can just take, and if you can see that by taking the average on both sides. So this just says that the average of e for any x is naught, so of course the average of e overall has to be naught as well, and again that follows by the law of iterated expectations. So this just means, and it simplifies down the proof, we have what we've got to show is, we have to show then, in this case, we've got sigma squared equals e of e squared, because this term equals naught, and sigma squared x simplifies down to e of e squared given x. Okay, so then we can show the result. Well, just use these two, which have followed from the assumptions, that assumption we made, which of course implies this, and then we've used that to simplify these down. We plug them into here to solve and simplify down. So then, well, we can establish it then. We take the average, again, with respect to x, of sigma squared x. Well, that just means plug in this. We've got, that's the e of e squared given x. Again, you sometimes can make it clearer to put actually we're taking the average with respect to x of this. And well, then that's it. So by the law of iterated expectations, this equals e of e squared, which is just sigma squared by definition. So this follows by definition of the law of iterated expectations. And it makes intuitive sense. We've got the average of e squared overall, and this just says we'll take the average of e squared for any fixed value of x, and then average over every possible value that x can take. So of course you're going to get back to the overall average of this variable e squared. So we can see in this model then that the average of the conditional variance is just equal to the unconditional variance. And it makes sense. This is the average variance in the whole population, and this is the average variance given in the population of just X, and then this takes the average across all possible populations. Or that's the way you can think about it. The next bit then is just renormalizing. So it's asking us to show that we can, under the CEF assumptions, namely, we've got y equal mx plus e, we've got e, and we've got the e of e again. So under these assumptions, equals 0, and the variance of e given x, sigma squared x. It asks us to show we can rewrite y. Well, this follows straightforwardly then, that we can rewrite it as this plus epsilon sigma x, where variance of epsilon given x equals 1. Well, all we're doing is renormalizing the variance, right? We can just define epsilon as e divided by sigma x. So we can always do this. We can always break up e into this sigma x and then everything that's left. So define this epsilon as e divided by sigma x. So we can just rewrite this e like this. So we can always do this. We can always just rewrite this in this form here. You just choose the epsilon to make the two equal to each other, and the one that's going to make this happen is this here. So this is the value of epsilon that makes these two equal to each other. So then we've got to show what, all we've got to show now is that this epsilon, the thing that links the two, by definition, has got variance 1 condition on x. And, well, just plug it in. So we've got the variance of epsilon given x equals, well, variance, put it in, it's e divided by sigma x given x. Well, we're conditioned on x, therefore x is fixed. So the sigma comes out, and again it's going to come out squared because we're taking the variance. So this is just a constant now, and all constants come out squared. We've got 1 divided by sigma squared x. So again, if you've got any questions, just write in the chat and I can stop and wind back. There is a slight delay, remember. So this comes out squared, and then we're going to get the variance of e given x. And by assumption, this is sigma squared x. So we're going to get sigma squared x divided by sigma squared x equals 1. And this is going to be for all values of x. Everything we're assuming here is for all values of x. So we should really say that all throughout, this is for all values of x. We're assuming this. So we can always write it in this form. This first assumption, again, remember, is just equivalent to saying that the conditional mean of y equals to some function of x, just call it mx, and then we can always rewrite the residual as, we can in essence just rescale it. We can write it as a function of some residual with variance, conditional variance equal to 1, and then this then will scale it to give it the right variance. Okay, so it's kind of like when you normalize a t-stat and kind of backing it back out again. So we're just renormalizing this to have mean 0 and variance 1. That's all that's going on there. So this is just general properties of, in essence, the conditional mean, the mean and the variance of y. We can always broadly rewrite this here, any y, as some function of x, and then everything else, this residual, and we can rewrite it in this form. So what this is saying is then, all we've got to do then is model what the function is for m. For example, it could be a linear function, and we've got to work out what is the form of the conditional variance sigma x. And this is when, so think of this at the broad level then. So before, we've not really said anything about the form of them. We just know that that's, we can always do that. For any y, we can always rewrite it in that form, and then all we've got to do then is to find the correct functional form for m and the correct functional form for sigma x. And that's when we start making these simplifying assumptions, and we start then with the linear model. We assume that m's the linear in parameters, and or name it just a linear function of x, in X, and then, well, it can be written, and then so for example, then the simple model of this, simplifying, taking a special case, this holds kind of generally, no matter what m and sigma are. There could be any complex functions of X. So the linear model then assumes that mx is linear in parameters x dash b. It can be written in that form, and then we may assume homoscedasticity. That would then assume sigma squared x is just a constant, and they assume this for all x. So again, you don't have to make both of these. We don't always have to make, again, these assumptions will give us different results. But for example, you might simplify down and say, okay, well, what happens if these two assumptions hold? Well, that just means then that y equals x transpose b plus epsilon sigma. This is just then a variable with mean naught and variance sigma squared. Okay, that simplifies things down a lot, because then we've only got to estimate one parameter to get the whole variance function, and we've just got to estimate these p parameters here. So then we've got p plus 1 parameters to estimate. Here, the problem technically is infinite dimensional, in that if we don't specify some restrictions on the form of m and the form of sigma, well, they could be any functions. They could be really complex, and they could have many. They could be infinite dimensional. So here, this obviously simplifies down a lot, but of course, then it requires a lot of assumptions to hold. So we're going to come back to this. We're going to go into detail on the linear model. So, but this just gives you the very broad brush idea of modeling this kind of the conditional expectation function of y. So rewriting y in this way, we can always kind of think of it in general. We can always break down y into this form, and then all that's left then is to specify forms for m and forms for sigma. So you might then move to nonlinear models where you allow more general nonlinear forms, and you may specify a form for this. So for example, you may specify that sigma squared x equals, say, exp x transpose b sigma, for example, or some call it delta, allow them to be different. So we could assume that if there wasn't homoscedasticity, we could say, okay, well, maybe it looks like this, that it's got this form here, and then we could estimate these, but we could come up with models to estimate these parameters. So, and you can actually do that by maximum likelihood. So we can start to talk about these models in a bit, but for now, we've been assuming that this is just constant. But bear in mind that we can actually specify not just different functional forms for the conditional mean function, but also different functional forms for the conditional variance function. Okay, so then the next question then, question 2. So this in essence is asking us to look at the assumptions that we make in the OLS model versus when we want to just show consistency versus what we need when we want to show unbiasedness. So the assumptions are stronger. You've seen the assumption phrased in two different ways. You've got the zero conditional mean assumption, and then you've got this assumption here, which is a weaker form. So the first part we can begin is asking to show that in a linear projection model ex. Well, this is pretty much by definition. So what this is saying is here, this x again in general will be a p by 1 vector. So it could be, call it x, and again we've dropped the I subscripts here to denote the sample, to denote the point in the sample. So x1 could be age, x2 could be gender, and so on down. There could be p variables. So this e of x times e equals naught, of course, well, this x is just equal to e of, we've got x1 times e, x2 times e, down to xp times e. That's saying that this equals naught. This is just equivalent to saying that all of these e xi times e is naught. We'll call it j for all j equals 1 to p. That's another way. This vector form just summarizes that saying that all of the x's satisfy this statistical orthogonality condition. So when we have a linear model, well, the projection, if we have y equals xb plus E. And assuming that this holds, well, what does it imply? If we enforce this, well, this just says that the beta is the E of x, x dash minus 1, E of x, y. So this is the linear projection. So what, and by, so all it's saying here is if you evaluate this at this linear projection vector here, that by construction this will hold, and it will by definition. They're kind of the same, it's a reverse way of saying the same thing really, and you can see that by plugging it in. So if we plug in, we've got y, we've got E in here, E equals y minus x b. Sorry, it should be x transpose times b. X transpose times b. Okay, so we've got a 1 by p vector of regressors transpose times a p by 1 vector of coefficients. Okay, this is a p by p matrix. This is p by 1, and again, it's going to give us that a p by 1 overall. Well, we can show it. What all we're showing is if we take this linear projection coefficient. This is the definition of it in the population model. So this is the population projection. You can do the same thing for the sample. You just have the sample averages. Well, we can. We're showing that all it means is if you evaluate this here at that we get that result. So it's just showing it the other way around. So plug it in, and then take expectations, multiply it by x. So x times e. We're going to get the x here. Expand it out. We'll get xy minus x, x dash beta, and we always left multiply here. In general, we always multiply on the left by a vector. So this is e, this is x times e in this linear model by definition, and then just show then plug in this beta. But first take the expectation. So e of xe, we'll plug it in. It's equal to e of xy minus x dash b. Again, it's the average of two terms. So again, it's the, and again they're both vectors, but the average of them two vectors added together is the average of each one added together. And the average of a vector, as I said, just takes the average of each element. So we're going to get e of xy minus e of x, x dash, and the beta comes out because it's constant. Okay, you can't take it over here, so this was kind of common. You can't put it there because it's not a scalar. Unless it's a scalar, you can't put it over this way. So this x dash, remember, always remember to check. So this is p by 1, this is 1 by p. So this here is also p by 1. You can't put it over there because it wouldn't work. You can't have a p by 1 times a p by 1. Okay, these two, they've got to be conformable. Okay, so be comfortable working with the definitions of vectors multiplication. If it's a scalar, of course, it doesn't matter whether you multiply on the right or the left because they're all 1 by 1. So it doesn't matter where you multiply by. Okay, so then we've got to show that this is not, and you can see straight off, once you plug this in, you're going to get not. So plug it in, evaluate it now at the projection coefficient. We're going to get e of xy minus e x dash, and then again we're going to plug in the projection coefficient, and you can see now what's going on. Well, this by definition of the inverse of a matrix is the identity matrix, and then the identity matrix times by a vector is itself. We're going to get e of xy minus e of xy equals not. So this is kind of swings and roundabouts. It's this condition that defines what the projection coefficient is. So of course, when you evaluate the linear model at the projection coefficient by design, you're going to find this statistical orthogonality. This here is the population projection. So of course, you don't know what that is. Very broadly speaking, think of these e's as taking the average in the whole population. The sample version is where you force the sample of this to hold. Instead of forcing the average in the whole population to be naught, you enforce it in the sample, and then you're going to get the sample equivalent of this population projection here. Okay, so that's the linear projection at the population level, and you can do it equivalently for the sample, and we'll see that. We'll come and talk about the sample projection. So the next question then, the next part of that was in essence asking you to verify, but what it's saying is that this here implies this, but not the other way around, but not the reverse. So it could have maybe been a bit clearer worded there, but it's saying that the assumption that we make in this is the linear projection assumption. If beta is such, so we've got a linear projection, in linear projection evaluated at the linear projection coefficient, then this holds, E of x times E equals naught. And it's saying, sorry, the other way around. This implies this, but not that. Sorry, it's this way around. What it's saying is that this zero conditional mean assumption implies this linear projection assumption, but not the reverse. So that this is a stronger assumption. And remember, very broad, we need this stronger assumption to hold, enable to establish unbiasedness. And this is what we need to show consistency. And we're going to come and talk about this. But in the conditional expectation function model, as it's defined in the lectures, we have that this E of y given x is equal to mx plus E, where the zero conditional mean assumption holds. So that's what you've seen in lectures as defined as the conditional expectation function model. Sorry, just E of y equals m of x. Sorry, just gonna wait. We've got y equals m of x plus E like this, where we assume this holds. This is what you've seen as the conditional expectation function model, which in essence just says, as we said earlier, that E of y given x is equal to m of x, is another way of saying it, putting these two things together. And what it's saying in essence, and whereas it's saying that does this, if we've got this assumption holding, does it imply this? Does it imply this stronger condition? Well, it doesn't necessarily. Namely, the linear projection model says y equals x dash beta plus E, where expectation of E times x equals naught. So that's the linear model with the linear projection assumption. And it's saying, in essence, this question is asking us to show that this assumption, if it holds in a regression, implies this, but not the other way around. And we can see the first way around, right? So we can see that the zero conditional mean assumption, E of E given x equals naught. Well, this holds, and again it holds for all x. This is the zero conditional mean, and we're going to show it implies this. Well, the x, we want to show then that E of EX equals naught under that assumption. So we're going to use this assumption to prove this here. So first of all, take the thing that we want to establish is naught. Then we can use the law of iterated expectations to break this up into two bits. The average over x of the average of this variable given x. So this is by, and again, always state the assumptions that you're using here by law of iterated expectations. Inside here, we're conditioned on x, so x is fixed, so this can come outside. So we'll then get E of x times E of E given x. And again, assuming this, that it equals naught for all x, and again it's crucial that it holds for all x, well then this is naught inside for every value of x, because remember we're taking the average of every possible value of x, so therefore the sufficient condition is that it's mean naught everywhere. This equals naught then. So this, and so we can see, you can kind of see here as well, and this was quite an issue with the earlier problems, the assess problem set, is that we don't actually, this is just a sufficient condition to prove this. We don't actually need that to be not everywhere. It could actually vary with x, but so long as the positives and negatives multiplied by x balance out, they could still equal not. So if this holds, then it will if this holds, it implies this, but it's not actually strictly necessary for this to be mean not. And that was a common mistake in the, you don't need it to hold, it's just a sufficient condition. The next thing is then to show that the reverse doesn't hold. And to do that, we just need to give a counterexample. So the next bit then was to have that, so we proved one way around. The next bit is, does E, we want to show that E of x, this condition does not imply that the expectation of E given x equals not. Well, there's many examples you can give. The common one is, assume that x is normally distributed not 1, just for simplicity. Normal not 1. And we have that the distribution of E given x is distributed normal with mean, say, x squared minus the mean of x squared. So this was it in the solutions, but in general, you should really have it centered. It's got mean not and variance whatever 1. It doesn't matter what the variance is. Can let it be variance 1. Well, in this case, then we can see that the E of E given x. Let's see that we first got to establish, of course, that E of xe equals not. In this case, which it will do. So we plug in E. Well, we can use, we're going to show this. Well, first off then, plug in, we're going to use the law of iterated expectations. So we can rewrite this as EX, E, again, it's the average over x of this variable given x. So we've used this before. Again, the x comes out because it's fixed in this inside the expectation. So we're going to get x e given x. And in this case, well, the conditional mean is just this. This is by definition the conditional mean of this normal variable. So the conditional, or you don't even need to assume it's normal really. You can just assume that the conditional mean is equal to this, which we always can do. So you can assume it's normal, or you can just assume the conditional mean is x squared minus the mean of x squared. So we can plug that in, and we'll get E of x, E of times this by x, and we're going to get x squared minus the mean of x squared. This was in the solution. One of you asked this in the class, which is a very good question. Is we want to scale this. We'll see this, but we want to subtract this off so that it's got unconditional mean not. Okay, so this here is then the condition. So we assume, in essence, you can assume it comes from a normal distribution, or you can just directly assume this, that the E of E given x is x squared minus the mean of x squared. And if we expand all this out, this equals, so again, take the expectation within. So again, we're going to get E of x. Where's the pen gone? We're going to get E of x. Expand it all out. We're going to get x cubed minus x times E of x squared, which will just be some constant number here inside. Again, we've got the average of two terms. This is just the average of x cubed minus the average of x times the average. Again, we should probably put a little e. Again, we often drop this, but you should really put a little. We often, for clarity, put a little subscript to make clear which distribution we're taking averages with respect to. You don't. Sometimes it's dropped, but sometimes it can make it clearer when you're working with the law of iterated expectations times e of x squared. And this is it. So because it's normal not 1, both of these are not. Or you can just assume that they're both not. So it doesn't have to be normal. If e of x is not, this is not. And if it's assume it's symmetric and mean not, well by definition that would be not as well. So e of x cubed can be not if the positive, because obviously x cubed for positive x is positive and x cubed for negative x is negative. And if if it's got mean not and if it's a symmetric distribution, then what we can show is that the average of this x cubed is not. So for any mean not symmetric distribution of x, we can show this result, and this will equal not. So what we've shown is, in the case where we've got the distribution of e for a given value of x is normal with this conditional mean and some variance. The variance doesn't have to be 1. Nothing would change if that was sigma squared or even a function of x. Okay, so the key bit then, we've shown that e of x equals not, but we can see, of course, that this condition doesn't hold. The zero conditional mean assumption doesn't hold, because of course, well, we just by definition, e of e given x is defined as x squared minus its mean, which of course is a function of x. E of x squared is just going to be some constant number, 10 or 5 or whatever, and of course x squared varies in x. So this isn't. So of course this doesn't equal naught for all values of x. It might do for it will do, or might do for one value of x, where x squared equals e of x. But of course it's got to be equal to naught for all values of x, and that's the definition of the zero conditional mean. So we can see we found an example where this linear projection assumption holds, or this kind of weaker exogeneity condition holds, that e and x is statistically orthogonal, but this zero conditional mean assumption doesn't hold, where the mean of e given x actually varies with x. The reason why we subtracted off the mean of x squared was to make sure that the average of e equals naught, which we often assume. Do you see what I'm talking about? He said the average of e has also got to equal naught. Or, well, this was one of the questions by one of you in the tutorial. If this x vector includes a constant, you've got other variables in there, well, this e of x e will imply that e of e equals naught. In essence, what it means is, and we know this already, if one of your x variables is a constant, it implies on this OLS assumption that the mean of e is naught. Okay, and we get that because when we're going to get x times e, all of these average will have average naught. So of course this implies that the first element of this vector will have mean naught, which is just e. So then for the linear projection assumption, where we include a constant, it implies that the mean of this e is naught, and the sample version of it means that if we include a constant, that the average of the sample residuals is naught, and that's by construction. So if we need that to hold, so if you just specify that e of e given x equals x squared, like in the solutions, well, this implies by the law of iterated expectations that e of e, which is just the e of x of e given x, is equal to e of x squared, which of course doesn't equal naught in general unless x is just a naught everywhere. Okay, which will be ruled out here. So it's just so if you don't include a constant, it's fine. But in general, we do include a constant in x, and if we include a constant in x, this condition implies that the mean of e is naught, and therefore in our example we need to make sure that the conditional that this e would have unconditional mean naught, and to achieve that we can just subtract off this mean of x squared to make sure it's got conditional mean equal to 0. Okay, so hopefully that's clear. So then, so we prove, so this just then, what we've seen is that this zero conditional mean implies this statistical orthogonality or this weaker exogeneity condition, but not the reverse. And it makes sense because what we're going to see is that this stronger zero conditional mean assumption is something that's going to be needed for unbiasedness, whereas this assumption is something that shows a weaker condition, which is a crucial condition to show consistency. So it's a stronger assumption, and it, in essence, broadly speaking, allows you to establish a stronger result. Okay, so then I think we're on now question 3. So derive the method of Momment's estimate of the variance of the random variable y. So this is relatively straightforward then. The variance of y, again, we've got the shorthand. Remember that this is just shorthand for saying this, which is the formal definition of the variance. It's the average of y minus its mean squared. Expand all this out, and we've got, again, so you should be very comfortable with these definitions by now. We've got e of y squared minus the mean of y all squared. Sorry, that's the bracket, and then all of the mean squared. That's that. So we can rewrite this as a moment condition. So remember, the method of moments, broadly speaking, just says you do the estimation where you replace a sample, you replace a population expectation with the sample expectation. So we can the method of moments here, call e of y mu, and call this variance of y sigma squared. Just for, again, just for shorthand. Well, what we've got is sigma squared, which is just shorthand for the variance of y. The thing we want to estimate is equal to e of y squared minus mu squared. And we've got also a moment condition for mu as well. We've got mu, of course, equals e of y. We can rewrite this as a moment condition. We can rewrite this as sigma squared minus y squared minus mu squared, and think of it as now as we're going to have a vector, and just mu minus y. Well, we can rewrite this. This is just the average of this equals 0. This just expands back out to the above. So this here inside this vector is the moment condition, the moment function, and the average of this equals 0 at the parameters of interest. So we need to, this variance of y is a function of the average of y squared, and we've got to estimate this mu parameter as well. So that's it then, and then you just do the sample version of it. So this is the population moment, which identifies the mean and the variance, because remember the variance is a function of the mean, so we've got to identify both of these parameters. So can you all see, if you expand this back out, you're going to get back to the two conditions above. So all the, and so so you can see it straight here. We can see then the sample version of this is just that we're going to have y minus mu, do it in our sample now, 1 over sigma I equals 1 to n equals 0. That's a sample analog of this one here. Then this is solved at mu hat equals y bar, and then we can do the one for the one above. We've got the average now, 1 over n sigma I equals 1 to n of sigma squared minus yi minus mu squared. Remember, this sample estimate is going to be mu hat. Got to evaluate this at mu and sigma, set this equal to 0, we can then rearrange, and you're going to get the sigma hat squared. The sample version is just going to be the sample average of y squared minus mu hat squared. This is just a really long-winded way of saying the method of moments just we've got the population version. We want to estimate this population variance sigma squared. Well, we replace the population average of y squared with its sample version, and we replace the population mean of y with its sample mean, mu hat x, which is just y bar, and plug them in. And you can see that just by writing it formally in this moment condition way, it's saying the same thing. All it says here is, in this equation, is to get the sample versions of these two here. Well, you can rewrite them as an equation like this, and then you can solve the sample version of them. So it's in essence just the same thing. Okay, so that's the method of moments. Broadly speaking, you replace the population condition, the population average, with the sample average. And then, so we've got then, I think we covered those, so we'll probably just do them again. So we've got consider the linear regression model, y equals, so we've got the standard, and again we're assuming x is scalar, so there's just one value of x, so it's an xi is a 1 by 1 vector, where x scalar, derived, and okay, in this particular question you didn't need this bit. To derive the Ols estimator, we don't need any assumption, it's just a definition. And remember, the definition of the Ols estimator is the minimizer of the sum of squared residuals. So again, if you go, think of this as the true parameter, call it beta naught, and we want to then find the Ols estimator of it. Well, we've got the true model yi equals xi beta naught plus ei, but it's kind of, well, it's kind of irrelevant in many ways what the true model is. The definition of the Ols estimator in general, it's the minimizer of the sum of squared residuals, and the residual of the linear, the residuals from the linear model. So this here is the residual at sample point I at beta in a linear model. So it's actually really irrelevant whether or not the true model looks like this, because the Ols estimator is defined as the minimizer of the sum of these squares, sigma I equals 1 to n. You can divide by n if you want, it makes no difference to the max, to the minimizer. So this here is a function of beta, sum of squared residuals, sample size n at beta. For every different beta, we're going to get a different sum of squared residuals, and it measures how far this predicted line is, this beta xi, from yi. Okay, and the definition is, so it's just to make clear that the definition of the Ols estimator is completely separate to whether or not the true model is a linear model. We can always work out what is the beta that minimizes the sum of squared residuals. The properties of that then will depend upon what the true form of y and x is, the relationship between y and x. So beta hat Ols, just to be fancy and write it in its formal way, just like we wrote the maximum likelihood estimator, it's the argument or the parameter that minimizes across beta the sum of squared residuals in the linear model. And again, this is a residual from the linear model. You can generalize this to a nonlinear model by allowing a nonlinear function here, and that would be the definition of nonlinear least squares. So for example, if you assumed a nonlinear model like this, say, well, you'd then construct the residual from this nonlinear function at beta, and then you could do a nonlinear. That would just be a nonlinear optimization problem then. Okay, so the definition of Ols is this, and just to again reiterate, that's the definition of it always. So it doesn't matter what the true model is, that's its definition, and its properties will then depend upon what the true conditional mean of y and x is. And we're going to come to this. So that's just a bit of background. You can generalize all of this to nonlinear least squares, very straightforward. So that's its definition. Well, then we know then we're going to find the first order condition, and in this case this is a scalar, so it's going to be simple to work out. There's just going to be one first order condition, and we don't need to use vector calculus. So you can generalize this when beta is a vector, but when beta is a vector, it just means you've got a first order condition for every beta, and you stack them all into a vector and you solve. So once you understand it for the scalar, i.e. one parameter and therefore one moment condition, one first order condition, then you understand it for the vector case. So to find the solution to this, well, we differentiate DSSRN beta over d beta, and find the parameter where this equals naught, and this is defined as beta hat OLS, because this is going to be the solution. And we can see here that this is a convex, strictly convex function, so that it's going to have a unique minimizer, so that the stationary point will find the minimizer of this function. It's just a quadratic here, a simple, it'll have one solution. Well, the first order condition will just differentiate the sum of squared residuals. We're going to get sigma. So again, you can apply the sum afterwards. First of all, differentiate the function and then take the sum after. So I mean, you should of course include the square, and then we're going to get, you're going to get sigma. The 2 will come out because it's constant, xi, and the you're going to get minus 2 xi yi minus xi beta. So you're just differentiating y minus beta x squared. You're going to get 2 times minus x, and then times the y minus bx, and then to apply the sum. Okay, so work out the derivative for any yx, for any residual, any I, and then sum across the i's, and anything that's constant comes out. So then if we solve and set this equal to naught, and that's going to then be, the solution will be beta hat OLS. Again, we can divide both sides by minus 2 because it will not affect the solution. So we can delete that. We can divide both sides by minus 2 and then solve. And you can see then we're going to get, it should be multiply it out, we're going to get beta hat equals sigma xi yi I equals 1 to n divided by sigma xi squared I equals 1 to n. So this is the Ols estimator in a one parameter, one regressor model. Okay, and we can see, for example, if the xi was a constant, if xi was equal to 1 or everywhere, so we just regress y in a constant, we can see this would be the sample mean. So that's a common example of a one regressor model where we just work out the sample mean. So you can think of that then. You can see if you plug in y xi equals 1, we're just going to get sum of y over n. So in this particular case, this is just to link it to show you the common example of a one parameter model when you just estimate the mean. You can think of that as a linear model just in a constant. You're going to get sigma yi over n if you evaluate this at xi equals 1. For all I, of course. Constant, so it's the same for all I. Okay. Again, it doesn't have to be a constant, and whatever x is, this would be the definition of the beta that would minimize the sum of squared residuals. And we can see this here is just the sample analog of the population version. So again, multiply both sides by 1 over n. It's not going to change anything, but we can see that this is the sample average of x times by the residual at beta hat. This here is just enforcing the population version of the linear projection model, which selected beta to make the population average of x and the residuals have mean naught. So this here is just the sample projection. Another way of thinking about this is the sample projection parameter. So remember, in the population version, we choose the projection is e of xi times by y minus xi b. It chooses this to be naught and it finds the beta, and remember, it's just all this is here, this population projection assumption. This just says that the average of x times by the residual, call it say beta naught, at the, let beta naught be the projection parameter that solves this. It makes x statistically orthogonal to y minus x beta naught, this residual. This just says that xi times this residual at the projection vector, or here's a scalar, has mean naught. And you take, this is in the population. This is the exact same thing. This just says that the sample average of x times by the residual at the sample projection has mean naught. Okay, and we talked about this in the first tutorial, this idea of a moment condition. So for example, if this holds, if beta naught, if this holds, if the true model's linear, and this assumption holds at the true parameter beta naught, if this E is unrelated to X on average in the population model, well, that will then define beta naught. And of course, to estimate beta naught, we just solve the sample version. And that's all. The reason why we do, another way of seeing this is the OLS assumption. The key one to get a consistency. If this holds at the true parameter beta naught, assume that we've included all the confounding factors and there's no bias, and that this exogeneity condition holds, well then we can solve for beta hat in our sample by solving the sample version. And the reason that's why we want to minimize the sum of squared residuals, the reason why the estimator from that will work well and be consistent under that assumption is because it's just solving the sample version of it. Okay, so that's we talked about this quite a lot in the first lecture, first tutorial. So then, okay, so I think that's it for that. So we're done for, and again, it all generalizes when X is a vector. When you take the first derivative, this X would be then a vector. So it's going to look very similar, but the derivative will be this, and you're going to have xi dash there. So it's going to be the same form, but now you're going to have a first order condition for every X, and you're going to stack them all into a vector, and you can solve for beta. Okay, so what is this orthogonality condition is? So another way of seeing it is, you can see it visually as well. When you've got yi, let's say we've got a sample of 2, and you got, say, y1 equal, I don't know, 2, and y1 equals 1. So you've got a sample, just to give you what, to see what this is, this sample projection. Why does this minimizer of the sum of squared residuals, why does it choose this beta to make this residual orthogonal to X? Well, you can see that visually in a geometric sense as well. Assume that you've got 2 sample points, and just take any arbitrary. Let's say that y1 is 2 and y sample point 2, y is 1. Well, we can write this as a vector. Well, it is a vector. Y, our sample, is a vector. It's 2 and 1. So you can write this, draw it in a diagram. Well, if this is 2 and this is 1, well, this would be our data point y, and you can then, we often draw an arrow right, so that it's defined from naught, and we've got this. So this should touch the naught here, the naught axis here. Okay, so then that's our data point y, and let's suppose then we've got x1 equals well, it doesn't really matter, x1 equals 1 and x2 equals let's say, you know, yeah, we've got a 1, let's say we just got one regressor x, and it takes value, say, 1 at sample point 1 and 1 at sample point 2, just for arbitrary. Then we've got one sample point, we've got one regressor x, which takes values 1 and 1. So we've got a sample size of 2, we've got one regressor x, this is all the data points of x, and this is all the data points of y. In that case then, well, we've now got our data point is here. So we can draw the arrow there. So this here is the direction of our sample data. We then take a model, we want to then find the best fit of this linear model, which you just again, remember, we're linking it back to the example, we've just got one regressor x. So in that case, the fitted line, or the linear model, is just beta x. Well, beta x just scales this vector up or down. This beta just scales this direction. If you set beta equal to 2, then we'll be out here. 2, 2. Well, I've obviously not drawn it right to scale, but as you scale beta, it's going to get bigger. So if you scale beta up, it's going to push out the vector. And the reason why we choose beta to make the residual y minus beta x orthogonal to x, well, the residual is the distance between y and beta x. So let's say we choose beta and make it bigger, it goes to here. So this could be beta x. And again, as you make beta bigger, you're going to increase this. You're going to make it go from 1, 1 to 2, 2. You're going to move it along this line. The minimum point from here, the distance between these two, beta x and y, is a residual. And the minimum distance is where this here is orthogonal to there, where this is perpendicular to this line here. Sorry, so it's going to be, if you think about walking along here, but choosing beta is equivalent to just going along and along, and we choose the point where we minimize the distance from our line to here, and we can see that's going to happen where it's orthogonal, where this is perpendicular to that line. So this here is our residual y minus beta x, and we can see if we was here, well, by Pythagoras that can't be the smallest distance because it's going to be further away than this point, and it can't be over here because this is also further a bigger distance. So we can see another way of thinking about this, you can see it visually, is that it's choosing this beta to make this fitted guess to y as near as possible to y. And that's another reason why we get this orthogonal, where you can give an intuition of this orthogonality condition, why this choosing beta to make this orthogonal to x, well, we can see that by definition, if it's perpendicular, it's orthogonal to this line. So again, you can give a geometric definition, a geometric interpretation as to why choosing beta to make the residual orthogonal to x solves this minimization problem. It gets beta x as near as possible to the y's. Okay, so I think we've got one left. So hopefully it's been helpful. So we can do some more. I am making the video clips. It's just they're taking forever. But using matrix algebra, show that in a linear projection model x-e hat. Well, okay, again, it should have given a bit more. It's taking this from the lecture notes. It's very similar to. It should define what these things are. By definition, right? Let's just make it. By definition, this e hat is the fitted value from. Just make another document. It's pretty much the last bit is pretty much just it just holds by pretty much definition. So let's just document. So we have. Wait a minute, it's taking what's there. So the last bit then is asking us. Let's just look at it again. It's saying. It's asking why. Using matrix algebra to show that a linear projection model, this here is a sample linear projection model, so it's very similar to the population one. Well, you just evaluate this at the sample projection vector made as opposed to the population one. Interpret the meaning. Well, this here, the meaning is that this is the first order condition from the for OLS in the general vector case. Okay, so when we take the sum of squared residuals in the vector case and differentiate vector beta, the first order condition will have that x, all of the x's stacked together, times y minus x beta equals naught. And the solution to this is then the Ols estimator. So this is the first order condition from minimizing sum of squared residuals, and we can see we just saw this in the simple case where x was a scalar. This here is the y, the vector of y's, so we're going to get a vector pointing to y and a vector pointing to x, and we're going to multiply it by its, the projection parameter. So the distance between these y minus xb is the residual, and in order to make this fit as xb fit as near as possible to y, we make it orthogonal to x. And this is just a definition of orthogonality, that x dash e equals naught. So again, you can show this by calculus, and again, it's very clearly written in the lecture notes in the book. So another way of seeing it as it's just the choosing b to make this residual from this line orthogonal to x. If you solve this, you'll of course find beta hat equals x transpose x minus 1 x dash y. That is then the sample projection vector for beta. So we can see straight away, it's the same thing. This defines beta hat, and you can do it then in reverse. So if you evaluate this at beta hat, of course you're going to find naught. So this just defines what beta hat is. This is the definition of this will give you the definition of the beta hat that is the linear projection in the sample case. Are there any other questions then? So I mean, we can have another one. We can do some more. Hopefully that was helpful. I am going to make some finished produced video clips. When you actually see what I'm making, you'll understand why it's taken a while. But for the ones that way, I won't have time probably to make a full finished video clip for each tutorial. But for the ones that we don't have a video clip for, we can run through. We can do more live streams, and again, before the revision, we can go through some past exam questions as well. That might be useful. So again, if you've got any questions, just ask and we can put it onto a live stream and do some more. I'll also save this video as well. Okay, so hopefully that was useful. So it'd be good to hear what you think about it. Sorry about the interruption at the beginning. I should, next time, there shouldn't be any glitches. Okay, so we'll leave it there, and I shall see you on Monday. See you later.